On April 14, 2010, a small island on the edge of the Arctic Circle woke up and began to cough. Beneath hundreds of meters of glacial ice capping Eyjafjallajökull, a column of magma had been silently rising for nearly 20 years. And when it erupted, it didn't just send ash into the sky, it sent ash into Europe's sky and froze an entire continent's aviation system solid. More than 100,000 flights cancelled over 6 consecutive days, roughly equivalent to shutting down every single flight corridor from New York to Los Angeles and back for an entire week with no warning and no fix. It was the first time since World War II that European skies fell completely silent, and no one had the power to order it to stop. So what exactly happened inside that mountain, and why did the ash from one small island have the power to paralyze the entire modern world? Iceland is an island born from fire, sitting directly on the junction between two of the North Atlantic's largest tectonic plates. The North American and Eurasian plates are slowly pulling apart at roughly 3/4 of an inch per year, about the same speed at which human fingernails grow. But Iceland doesn't just sit on a spreading ridge, it also sits directly above an unusually powerful hotspot, a rising column of magma punching up from deep in the mantle. The result is Europe's highest density of volcanoes, with over 130 volcanic systems, roughly 30 of which remain active today. Eyjafjallajökull sits in southern Iceland, its name meaning the glacier of the island mountains, and that is exactly what it looks like. A flat-topped mountain buried under a permanent ice sheet. Beneath that ice sits a caldera 3 to 4 kilometers wide, holding a magma chamber that had been dormant since its last major eruption in 1823. From the early 1990s, Icelandic seismometers had been recording small but unusual tremors beneath Eyjafjallajökull. In January 2010, small earthquakes began occurring with increasing frequency, a clear signal that magma was on the move beneath the surface. On March 21, 2010, Eyjafjallajökull woke with a small flank eruption on its eastern ridge, the Fimmvörðuhálsfasi, relatively harmless and initially treated as an early warning the system could manage. Local people even organized hiking trips up the mountain to watch the lava, because the eruption looked spectacular and seemed perfectly safe from a distance. But just below, a second magma chamber was building pressure, and it wasn't located on the flank, but directly beneath the thickest part of the glacier cap itself. That is what made Eyjafjallajökull different from almost any ordinary volcanic eruption. Water was its secret weapon. When magma at over 1800 degrees Fahrenheit contacts thick glacial ice, water vaporizes instantly and triggers a specific type of blast known as a phreatomagmatic eruption. Unlike a standard eruption producing coarse ash, this type of blast grinds magma into particles so fine they are nearly invisible to the naked eye. And those particles, once they reach the upper troposphere at 25 to 40,000 feet, could travel thousands of miles without ever falling back to Earth. The night of April 13th, Icelandic seismometers began recording signals that were entirely different, stronger, deeper, and continuous. At 1 in the morning on April 14th, magma reached the base of the ice sheet, and within minutes, Iceland would create the largest ash cloud Europe had seen in a century. At 1:30 in the morning on April 14th, the first explosion tore through the glacier cap of Eyjafjallajökull and launched an ash column 8 kilometers, roughly 26,000 feet, into the dark sky above Iceland. That column contained hundreds of millions of tons of ultrafine silica particles, hot enough to vaporize surrounding moisture and generate a full electrical storm inside the cloud itself. Simultaneously, the magma was melting hundreds of millions of tons of glacial water above it, and all of that water began cascading down into the Markarfljót river valley below. Within 2 hours, the Markarfljót river flow surged to a rate comparable to the combined flow of the Mississippi and Missouri rivers at peak spring flood, compressed into a single hour. The Markarfljótbrú Bridge, The critical link connecting southern Iceland's farming communities to the rest of the country was swept away completely within 15 minutes of the flood's arrival. Try to picture what that means. Not just your house is flooded, but the only road an ambulance could reach you on, the only escape route out, has just vanished under the surge. Around 800 local residents were evacuated urgently that night, many moving across dark fields in ash rain that was beginning to fall from the eruption column above. But that was only the first chapter of the disaster, because while Icelanders were managing the floods, something far more disruptive was silently drifting east. The jet stream at 30,000 to 40,000 feet was blowing southeast at 120 to 180 miles per hour, carrying the entire ash mass directly toward the most congested airspace on Earth. By the morning of April 15th, the UK's Civil Aviation Authority issued a decision that had no peacetime precedent in the history of commercial aviation. All United Kingdom airspace was closed, all flights banned from taking off or landing, effective immediately and with no defined end date. The core problem was that volcanic ash is nothing like rain or fog. Aircraft cannot fly through it for reasons that are catastrophically dangerous from an engineering standpoint. Jet engines operate at between 1800 and 2500 degrees Fahrenheit, well above the melting point of volcanic ash, which liquefies at around 1500 degrees Fahrenheit. Ash enters the engine, melts into molten glass, coats the turbine blades, and can bring the entire engine to a complete flameout within minutes, sometimes seconds. History had a precedent. In 1982, a British Airways aircraft lost all 4 engines flying through ash from Indonesia's Galunggung volcano and came terrifyingly close to not making it back. On April 15th, 9 European countries closed their airspace within the first 24 hours, and that number grew to 23 countries within days. Within 48 hours, European airspace went from the densest flight network on Earth, with tens of thousands of daily flights, to a near-total void. Imagine the entire interstate highway system of the continental United States shutting down simultaneously, with no detour and no timeline for reopening. Over 10 million passengers were stranded across the globe, many with no money left, no accommodation, and no information on when their flight would ever depart. The European aviation industry lost an estimated $1.3 billion in the first week alone, roughly equivalent to the entire annual GDP of a small nation. And this was not just a story about cancelled holidays, this was a story about global supply chains being severed overnight. Factories across Europe that relied on air-freighted components from Asia began halting production lines because the parts simply weren't arriving. Kenya alone was losing an estimated $1.3 million every day simply from cut flowers that couldn't reach European markets. All the while, above Iceland, the ash column continued erupting at a rate of roughly 200–300 metric tons per second at its peak output. Icelandic farmers within 30 kilometers, roughly 20 miles, of the volcano had to bring livestock indoors and cover animals' nostrils with damp cloth to prevent them inhaling ash. Ash fell so thickly that in some areas it formed a layer nearly 5 inches deep on the ground, heavy enough to collapse the roofs of local farmhouses. Scientists from the University of Iceland and the British Geological Survey deployed immediately to collect ash samples, feeding analysis into atmospheric models, trying to predict where the cloud would move next. But the problem was that the computer models available at the time were designed to forecast weather, not volcanic ash, and they were producing inconsistent results. At 8 to 12 kilometers altitude, the ash was too thin and dispersed to see with the naked eye, but thick enough to destroy a jet engine in minutes. This was the scenario aviation had never faced at this scale, an invisible hazard, impossible to measure precisely, spread across an area the size of the entire continental United States. By April 17th, pressure from airlines, governments, and stranded passengers was mounting to the point where regulators were being forced to reconsider their entire approach. Airlines argued that the ban was overly cautious, that the ash had actually thinned below dangerous concentrations in many zones, and that aircraft could safely fly through certain corridors. Several airlines conducted their own test flights, and post-flight engine inspections consistently found measurable erosion damage on turbine blades, even on aircraft that had operated in lower concentration zones. While governments, airlines, and scientific agencies debated, the ash cloud continued its movement, completely indifferent to every meeting and negotiation happening below it. On April 20th, after 6 days of closure, European nations began reopening airspace in phases under a new and more complex protocol that zoned hazard levels by measured ash concentration. But Eyjafjallajökull had no intention of stopping. The eruption continued until October 23, 2010, a total of 179 continuous days of activity. In the weeks that followed, European aviation operated in a state of continuous uncertainty, with recurring partial closures each time fresh ash pulses moved across the airspace. Air traffic control centers in London, Paris, Frankfurt, and Amsterdam were coordinating in real time an enormously complex system routing thousands of flights through airspace that expanded and contracted hour by hour. Every flight had to be rerouted, many adding hundreds of miles of deviation to the south, burning extra fuel, adding time, and adding significant operating cost to every journey. In total, across the most acute phase from April 15th to April 20th, more than 110,000 flights were cancelled, more flights grounded than at any other time in the history of commercial aviation. Let that number truly land. 110,000 flights, roughly equal to every single commercial flight that departed from the entire eastern seaboard of the United States over a full month, gone in 6 days. Inside Iceland itself, the local situation remained severe, with accumulated ash contaminating drinking water sources, destroying crops, and threatening the health of livestock across the south. Eyjafjallajökull's much larger and far more dangerous neighbor, the Katla volcano, began showing increased tremor signals, forcing scientists to monitor 2 volcanoes simultaneously with growing concern. Because in Iceland's geological history, every time Eyjafjallajökull has erupted, Katla has followed within months, and Katla is capable of producing 10 times the ash volume of Eyjafjallajökull. The entire European geoscience community began monitoring Iceland with a level of collective anxiety that had no peacetime equivalent. Katla did not ultimately erupt in 2010, but the question of when it will awaken remains open, and it remains open to this day. Returning to the ash cloud, post-event analysis showed Eyjafjallajökull's cloud contained unusually high particle concentrations at specific atmospheric layers, with the most dangerous zone sitting precisely at standard cruise altitude between 30,000 and 40,000 feet. The silica particles in Eyjafjallajökull's ash also had an unusually high silica dioxide content of around 55%, making them particularly reactive with hot engine metal surfaces. This meant even zones with ash concentrations below the old safety threshold were potentially capable of causing serious engine damage after extended flight hours of continuous exposure. It was the most severe test European aviation had ever faced in peacetime, and it exposed a massive gap in the continent's entire approach to natural disaster contingency planning. On April 20th, Europe's skies began reopening, but the aviation industry the world had known before April 15th would never operate in quite the same way again. Because in those 6 days, the world had learned a lesson no computer simulation could have taught, that nature does not read our emergency response manuals. And above Iceland, the geothermal furnace continued without pause, entirely indifferent to every human decision, meeting, and anxiety playing out below. This was not the deadliest disaster of the 21st century in human casualties, but it was the single natural event with the widest economic reach in the entire history of commercial aviation. Total direct economic losses were estimated between $1.3 and $2 billion from the airspace closure alone, before accounting for the cascade effects on global trade and tourism that lasted weeks longer. But the most significant impact of Eyjafjallajökull was not the money lost, but what it revealed about the absolute dependence of the modern world on a single interconnected aviation network with no meaningful backup. Thousands stranded abroad attempted to return home by train, ferry, and car, demonstrating that when aviation stops, no other system can replace it at equivalent scale. European high-speed trains, night rail services, and channel ferry crossings sold out within hours of the airspace closure announcement, their combined capacity handling only a tiny fraction of the cancelled flight volume. And beyond stranded passengers, Eyjafjallajökull disrupted medical cargo flights carrying vaccines, emergency equipment, and critical supplies that depended entirely on the aviation network. The European Space Agency and international scientific bodies deployed MODIS satellites and ground-based LiDAR instruments to track the cloud, building the most detailed volcanic ash observational dataset in scientific history. The total ash volume ejected across the entire eruption was estimated at roughly 250 to 270 million cubic meters, enough to fill approximately 100 Rose Bowl stadiums in Pasadena to the brim. And through all of that, the most remarkable thing is that Eyjafjallajökull is not Iceland's largest volcano, nor its most powerful. It was simply the wrong volcano in the wrong location at the wrong moment in atmospheric history. The combination of thick glacier ice, a particular magma chemistry, location directly beneath a powerful jet stream, and the fact that it sat directly upwind of the world's most congested airspace turned a modest eruption into a global crisis. As Europe's skies gradually reopened through late April, the world began assessing total damage and recognizing that what had happened was far more significant than cancelled flights. In Iceland, local farmers used heavy machinery to clear ash from their fields, with some areas taking 3 to 6 months before grass began regrowing through the deposit. Groundwater and surface water in southern Iceland remained contaminated with ash for weeks, with fluoride and sulfur concentrations exceeding safe limits for both humans and livestock. But outside Iceland, the most significant lasting impact was not material but conceptual, a recognition of the fragility of the global aviation system and the enormous gap in volcanic ash emergency protocols. Immediately after the crisis, Aerocontrol and national aviation authorities began building a new 3-zone hazard classification system to replace the all-or-nothing rule that had caused the total closure. The new system defined ash concentrations in micrograms per cubic meter of air, with 3 specific thresholds allowing restricted or full flights based on actual measurements rather than purely on computer model forecasts. In total, more than 22 European nations updated their natural disaster response plans within 12 months of Eyjafjallajökull, all targeting the blind spots the crisis had exposed. For Iceland and the local communities around Eyjafjallajökull, recovery was slow and challenging, but they carried with them an experience no one else on Earth had. They were a community that had lived with volcanoes for centuries, knowing how to evacuate quickly, how to rebuild, and knowing that the earth beneath them had never been and would never be fully quiet. Paradoxically, the Eyjafjallajökull crisis also created a rare scientific opportunity. Data collected during the event accelerated volcanic ash and aviation research by decades compared to the normal pace of scientific progress. Researchers at the University of Iceland, Imperial College London, and dozens of other institutions are still analyzing 2010 data and publishing new findings to this day. Geographically, the summit of Eyjafjallajökull changed permanently, with the caldera now visibly wider and the glacier cap measurably thinner than it was before the eruption. And the largest question the event left behind is not about Iceland, but about other parts of the Earth, because Eyjafjallajökull proved that a single volcano in the right position is sufficient to paralyze the modern world. The Eyjafjallajökull crisis was also the first time social media played a major role in communicating and coordinating response to a continental-scale natural disaster, signaling a new era in crisis management. Millions tracked ash movement in real time through Twitter and flight tracking applications, creating a virtual community of stranded passengers sharing information and response strategies in ways no previous generation of travelers could. Looking back from more than 15 years later, Eyjafjallajökull permanently changed 4 core fields: volcanology, aviation protocol, atmospheric modeling, and the way the entire world thinks about natural hazard risk in an interconnected global system. And if Eyjafjallajökull, a mid-sized volcano by any geological measure, could paralyze Europe for 6 days, then the question that naturally follows is, what happens when a larger one wakes at the same moment? In the aftermath of Eyjafjallajökull, the world aviation industry went through its largest natural disaster protocol reform in history, with over 70 nations updating volcanic ash response standards. Europe invested hundreds of millions of euros in new volcanic ash monitoring networks, including ground-based LiDAR stations, dedicated monitoring aircraft, and a network of atmospheric measurement buoys across the North Sea. The World Meteorological Organization's Volcanic Ash Advisory System was comprehensively modernized, with 9 volcanic ash advisory centers worldwide equipped with new atmospheric modeling capabilities. But despite all those improvements, scientists continue to warn that many of the world's active volcanic zones remain poorly monitored, particularly submarine volcanoes and those in developing nations. Taal Volcano in the Philippines, Mount Merapi in Indonesia, and the Cascades Volcanic Arc of Western North America all sit near major flight corridors and remain potential hazards comparable to Eyjafjallajökull in their aviation risk profile. Particularly notable is the Yellowstone Volcanic System in Wyoming, one of the world's largest supervolcano complexes, sitting at the heart of North America and continuously monitored by the United States Geological Survey. Eyjafjallajökull reminds us that in today's globally connected world, a single geological event in a remote corner of the planet can trigger a cascade of effects across the entire interwoven economic and transport system humanity has built. And that applies not just to aviation, but to medical supply chains, food systems, energy networks, and every infrastructure system the modern world depends on invisibly every single day. When the Hunga Tonga Hunga Ha'apai volcano in the Pacific erupted in January 2022, global aviation authorities were able to respond significantly faster and more precisely because of what Eyjafjallajökull had taught. The lesson of Eyjafjallajökull is not that we failed in 2010, but that every time this planet reminds us of its power, we have the choice to become wiser. Because in the end, the ash of Eyjafjallajökull did not just close Europe's skies for 6 days, it forced the world to look directly at a truth we tend to forget in the flow of modern life. That this planet existed 4 billion years before we built our first airport, and the sky has never truly belonged to us. We are only borrowing it while the ground beneath sleeps.